Picture this, deep in the heart of the cosmos, forces so immense they defy imagination are at work. Pressures so extreme they can crush matter into forms we can barely comprehend, reshaping the very fabric of the universe. These are not just numbers on a scale, they are the architects of stars, the destroyers of worlds, and the silent rulers of the cosmos. Welcome to a journey where we uncover the universe's most extreme pressures, forces so powerful they challenge everything we know about physics and reality itself. In this video, we'll explore 25 mind-blowing facts about these cosmic extremes, from the crushing cores of neutron stars to the explosive fury of supernovas. By the end, you'll not only understand the science behind these incredible phenomena, but also gain a newfound appreciation for the sheer scale and mystery of the universe. So, are you ready to dive into the depths of space and uncover the secrets of its most extreme pressures? Let's begin. Now, let's zoom in on one of the most extreme environments in the universe, the core of a neutron star. Imagine taking the mass of our Sun and squeezing it into a sphere no larger than a city. The result, a neutron star where the pressure is so intense that atoms are crushed out of existence. At the core, matter is compressed to densities so extreme that protons and electrons merge, forming a sea of neutrons. This isn't just dense, it's a state of matter so exotic that scientists can only recreate it in the most advanced particle colliders on Earth. The pressure here is so immense that a single teaspoon of neutron star material would weigh billions of tons, but it doesn't stop there. This crushing force creates conditions where matter behaves in ways that defy our everyday understanding of physics. Neutron stars are not just extreme, they're cosmic laboratories offering us a glimpse into the universe's most mysterious and powerful forces. And as we'll see, they're just the beginning of the universe's most extreme pressures. Now, let's turn our attention to another cosmic heavyweight: black holes. These mysterious objects are so dense that their gravitational pull is strong enough to trap even light itself. At the heart of a black hole lies the singularity, a point where gravity becomes infinitely strong, and the laws of physics as we know them break down. Surrounding this singularity is the event horizon, the point of no return. Once anything crosses this boundary, there's no escape, not even for light. The gravitational pressure near a black hole is so extreme that it warps the very fabric of space-time, bending it like a rubber sheet under immense weight. This distortion creates bizarre effects such as time dilation, where time slows down dramatically for an observer near the black hole compared to someone far away. But perhaps the most dramatic phenomenon is spaghettification. As objects get closer to a black hole, the difference in gravitational pull between their near and far sides becomes so extreme that they're stretched into long, thin strands like cosmic spaghetti. Black holes are not just destructive forces, they're also windows into the most extreme conditions in the universe, where gravity reigns supreme and the rules of physics are pushed to their limits. And as we'll see next, the universe has even more extreme pressures waiting to be explored. Now, shifting our gaze from the crushing gravity of black holes, let's explore another cosmic marvel: white dwarfs. These stellar remnants are the dense cores left behind after stars like our Sun exhaust their nuclear fuel and shed their outer layers. What makes white dwarfs truly fascinating is the extreme pressure within them. A pressure so intense that it defies the natural tendency of matter to collapse under gravity. This pressure is known as electron degeneracy pressure, and it's a quantum mechanical phenomenon that occurs when electrons are packed so tightly together that they resist further compression. Imagine trying to squeeze a balloon. No matter how hard you press, the air inside pushes back. In white dwarfs, electrons behave similarly, creating a force that counteracts gravity and prevents the star from collapsing further. This delicate balance between electron degeneracy pressure and gravity is what keeps white dwarfs stable, allowing them to shine faintly for billions of years. Despite their small size, often no larger than Earth, white dwarfs pack a mass comparable to that of the Sun, making them incredibly dense. A single teaspoon of white dwarf material would weigh several tons. These stellar remnants are not just relics of the past, they're also a testament to the universe's ability to balance extreme forces in ways that challenge our understanding of physics. And as we'll see next, the cosmos has even more astonishing pressures waiting to be uncovered. Now, let's turn our attention to the heart of our solar system, the Sun. At its core, the Sun is a powerhouse of unimaginable pressure and energy. Here, temperatures soar to around 15 million degrees Celsius, and the pressure is so immense that it crushes hydrogen atoms together, forcing them to fuse into helium. This process, known as nuclear fusion, is what powers the Sun and, by extension, our entire solar system. The pressure at the Sun's core is so extreme that it overcomes the natural repulsion between atomic nuclei, allowing them to collide and release vast amounts of energy. Every second, millions of tons of hydrogen are converted into helium, releasing energy equivalent to billions of nuclear bombs. This energy radiates outward, providing the heat and light that make life on Earth possible. Without the Sun's core pressure, nuclear fusion would cease, and the Sun would no longer shine. It's this delicate balance of pressure and temperature that sustains the Sun's energy output, ensuring the stability of our solar system for billions of years. The Sun's core is not just a marvel of physics, it's the very engine that keeps our cosmic neighborhood alive. And as we'll see next, the universe holds even more extreme pressures that continue to push the boundaries of our understanding. Now let's journey beyond the Sun and into the explosive final moments of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, it doesn't fade quietly, it goes out with a bang, and not just any bang. A supernova explosion is one of the most violent and energetic events in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. At the heart of this cataclysm lies unimaginable pressure, so intense that it crushes the star's core, triggering a shock wave that rips the star apart. This pressure is so extreme that it forces atoms to collide with such force that they fuse into heavier elements like gold, uranium, and even the iron in your blood. These explosions are so powerful that they can outshine entire galaxies for a brief moment, scattering these newly forged elements across the cosmos. Without supernova, the universe would lack the building blocks for planets, life, and even the stars themselves. It's a reminder that even in destruction there is creation, a cosmic cycle of pressure and rebirth that shapes the very fabric of the universe. And as we'll see next, these extreme pressures don't just shape stars, they also played a crucial role in the birth of the universe itself. Now, let's rewind the cosmic clock to the very beginning, the Big Bang. In the earliest moments of the universe, pressures were so extreme that they defy comprehension. Picture this: the entire universe was compressed into a space smaller than an atom, with temperatures and densities so high that the laws of physics as we know them barely applied. This unimaginable pressure didn't just exist, it was the driving force behind the rapid expansion of the universe, a process known as inflation. In less than a blink of an eye, the universe grew exponentially, stretching from a tiny point to a vast expanse. But the story doesn't end there. These extreme pressures also set the stage for the formation of everything we see today. As the universe expanded and cooled, tiny fluctuations in pressure and density began to emerge. These fluctuations, no larger than ripples on a pond, were the seeds of future galaxies and cosmic structures. Over billions of years, gravity amplified these ripples, pulling matter together to form stars, galaxies, and the intricate web of the cosmos we observe today. What's truly remarkable is that these early pressures didn't just shape the universe, they left behind a fingerprint. The cosmic microwave background radiation, often called the afterglow of the Big Bang, carries the faint echoes of those primordial pressures. It's like a snapshot of the universe's infancy, revealing the conditions that set everything in motion. Without these extreme pressures, the universe as we know it, with its galaxies, stars, and planets, simply wouldn't exist. And as we'll see next, these pressures didn't just shape the early universe, they continue to influence the cosmos in ways we're only beginning to understand. Now let's shift our gaze closer to home, to the colossal gas giants that dominate our solar system. Jupiter and Saturn, with their swirling storms and massive atmospheres, are more than just beautiful, they're laboratories of extreme pressure. Deep within these planets, the pressures are so intense that they transform ordinary hydrogen into something extraordinary, metallic hydrogen. Imagine the weight of an entire planet pressing down, layer by layer, until the hydrogen gas we know becomes a shimmering, metallic fluid. This isn't science fiction, it's the reality inside Jupiter and Saturn. At these crushing pressures, hydrogen atoms are squeezed so tightly that their electrons break free, creating a sea of charged particles. This metallic hydrogen isn't just a curiosity, it's a key player in generating the powerful magnetic fields that surround these gas giants. But the surprises don't stop there. As we delve deeper, the pressures continue to rise, creating even more exotic materials. Scientists believe that beneath the metallic hydrogen layer, there could be a core of super-compressed rock and ice, subjected to pressures millions of times greater than what we experience on Earth. These extreme conditions might even give rise to forms of matter we've never seen before, challenging our understanding of physics. What's truly fascinating is how these pressures shape the behavior of gas giants. They drive the intense storms like Jupiter's Great Red Spot and influence the intricate ring systems of Saturn. Without these extreme pressures, the gas giants would be entirely different worlds, and our solar system would lose some of its most awe-inspiring wonders. As we continue our journey through the universe's most extreme pressures, we'll see how these forces shape not just planets, but the very fabric of space itself. Now let's venture into the swirling chaos of accretion disks, where the universe's most extreme pressures meet the raw power of gravity. These disks, often found encircling black holes and neutron stars, are more than just cosmic debris. They're dynamic, high-energy environments where matter is stretched to its limits. Picture a whirlpool of gas and dust spiraling inward at incredible speeds, heated to millions of degrees by the sheer force of friction and pressure. At the heart of an accretion disk, the pressure is so intense that it compresses matter into a superheated plasma, glowing with radiation across the electromagnetic spectrum. This isn't just heat, it's energy on a scale that defies imagination. The pressure within these disks is so extreme that it can accelerate particles to nearly the speed of light, creating jets of energy that shoot out from the poles of black holes and neutron stars. These jets, powered by the immense pressure and magnetic fields, can stretch across thousands of light years, shaping entire galaxies in their wake. But what makes accretion disks truly fascinating is how they balance on the edge of destruction. The pressure within them is constantly battling gravity, creating a delicate equilibrium that can tip at any moment. When too much matter accumulates, the disk can become unstable, leading to explosive outbursts of energy that light up the cosmos. These events, known as flares, are some of the most energetic phenomena in the universe, releasing more energy in seconds than our Sun will emit in its entire lifetime. Accretion disks are not just cosmic curiosities, they are windows into the extreme physics of the universe. They teach us how matter behaves under conditions we can't replicate on Earth, and they reveal the intricate dance between pressure, gravity, and radiation. As we continue to explore these high-pressure environments, we uncover new insights into the forces that shape the cosmos, reminding us just how dynamic and unpredictable the universe can be. Next, we'll turn our attention to another extreme state of matter, one that existed just moments after the Big Bang, quark-gluon plasma. Now, let's step back in time to the very beginning of the universe, where matter existed in a state so extreme that it defies everything we know about physics today. This brings us to quark-gluon plasma, a primordial soup of particles that filled the cosmos just moments after the Big Bang. Imagine a universe so hot and dense that protons and neutrons hadn't even formed yet. Instead, the building blocks of matter quarks and gluons floated freely in a seething, chaotic sea of energy. This is quark-gluon plasma, a state of matter where the pressures were so immense that they tore apart the very fabric of atomic structure. To recreate this extreme environment, scientists turned to some of the most powerful machines ever built, particle colliders. Facilities like the Large Hadron Collider smash atomic nuclei together at nearly the speed of light, generating temperatures over 100,000 times hotter than the core of the Sun. In these collisions, the pressure becomes so intense that protons and neutrons melt, releasing quarks and gluons into a fleeting, fiery plasma. For just a fraction of a second, the conditions of the early universe are reborn, allowing researchers to study this exotic state of matter. What makes quark-gluon plasma so fascinating is how it behaves. Unlike the matter we're familiar with, this plasma flows like a perfect liquid with almost no resistance. It's a state where the fundamental forces of nature, strong, weak, electromagnetic, and gravitational, were unified, offering clues about how the universe evolved from a hot, dense soup into the structured cosmos we see today. By studying this plasma, scientists are piecing together the story of how matter itself came to be, revealing the incredible pressures that shaped the universe in its first microseconds. As we continue to explore quark-gluon plasma, we're not just uncovering the secrets of the early universe, we're also pushing the boundaries of human knowledge. These experiments remind us that the universe is far more dynamic and mysterious than we often realize. Next, we'll dive into another extreme cosmic phenomenon, the mind-bending magnetic pressures of magnetars, where the universe's most powerful magnetic fields come to life. Now, let's turn our attention to one of the most extreme and enigmatic objects in the cosmos, magnetars. These are not your average neutron stars. Imagine a star so dense that a teaspoon of its material would weigh billions of tons, and then add the most powerful magnetic fields in the universe. That's a magnetar, a cosmic powerhouse where the pressures are so intense that they warp the very fabric of space and time. Magnetars are born from the explosive deaths of massive stars, leaving behind a core so compressed that it becomes a neutron star. But what sets magnetars apart is their magnetic fields, which can be 1,000 trillion times stronger than Earth's. To put that into perspective, if a magnetar were located halfway between the Earth and the Moon, its magnetic field would erase the data on every credit card on our planet. These unimaginable magnetic pressures create an environment where the laws of physics as we know them are pushed to their limits. The energy released by magnetars is equally staggering. When their magnetic fields shift or crack under the immense pressure, they unleash bursts of energy so powerful that they can outshine entire galaxies for a fraction of a second. These bursts, known as starquakes or magnetar flares, are among the most violent events in the universe. In 2004, a magnetar flare from 50,000 light-years away was so intense that it temporarily disrupted Earth's upper atmosphere despite being halfway across the Milky Way. What makes magnetars even more fascinating is how they challenge our understanding of matter. Under such extreme magnetic pressures, atoms are stretched into long, thin shapes, and the behavior of particles becomes utterly bizarre. Scientists believe that studying magnetars could reveal new insights into the nature of matter, gravity, and even the possibility of exotic states like quark matter. As we continue to observe these cosmic giants, we're reminded of just how extreme and unpredictable the universe can be. Magnetars are a testament to the incredible forces at work in the cosmos, forces that continue to push the boundaries of what we thought was possible. Next, we'll venture into the vast expanses of space to explore the pressures within the interstellar medium, where the birth of stars begins. Now, let's shift our gaze to the vast and dynamic spaces between the stars, where the interstellar medium holds secrets to the birth of new worlds. The interstellar medium is the cosmic canvas on which stars are painted, a mix of gas, dust, and energy that fills the gaps between stars. But don't let its seemingly empty appearance fool you. This medium is a place of extremes, where pressures vary dramatically from one region to another. In the vast, dark voids of space, the pressure is incredibly low, almost a perfect vacuum. These regions are so sparse that a single atom might travel for miles before encountering another. Yet, even in these near-empty spaces, the interstellar medium plays a crucial role, acting as a reservoir for the raw materials that will one day form new stars and planets. On the other end of the spectrum are the dense molecular clouds, where the pressure is much higher. These clouds are the nurseries of the universe, where gravity begins to pull gas and dust together, creating the conditions for star formation. Inside these clouds, the pressure builds as particles collide and clump together, eventually reaching a point where nuclear fusion ignites, giving birth to a new star. It's here, in these high-pressure regions, that the magic of creation unfolds. The interstellar medium is also a place of constant motion and change. Shockwaves from supernova explosions or the collision of galaxies can compress the gas and dust, increasing the pressure and triggering the formation of new stars. These events ripple through the medium, shaping the structure of galaxies and influencing the evolution of the cosmos. What's truly fascinating is how these varying pressures interact. The low-pressure voids and high-pressure clouds are not isolated. They are part of a delicate balance that drives the cycle of star birth and death. Without the interstellar medium and its range of pressures, the universe as we know it would not exist. As we explore these cosmic landscapes, we gain a deeper appreciation for the forces that shape the universe. From the quiet emptiness of the voids to the bustling activity of star-forming regions, the interstellar medium is a testament to the dynamic and ever-changing nature of space. Next, we'll dive into the pressures that drive the formation of protostars, where the journey of a star truly begins. Now, let's zoom in on one of the most critical stages in the life of a star, the birth of a protostar. This is where the interstellar medium's raw materials begin their transformation into something extraordinary. As gravity takes hold, the gas and dust within a molecular cloud start to collapse inward, creating a dense, swirling core. This is the beginning of a protostar, a young star in the making. The pressure inside a protostar is immense as gravity relentlessly compresses the gas and dust into an ever-shrinking space. Imagine squeezing a balloon with all your might, except here, the forces at play are on a cosmic scale. As the material collapses, the temperature and pressure at the core rise dramatically. At first, the pressure is primarily due to the sheer weight of the collapsing material, but as the core heats up, thermal pressure begins to push back against gravity. This delicate balance between gravity and pressure is what defines the protostar's journey. If gravity wins, the collapse continues and the core becomes denser and hotter. But as the temperature climbs, the particles inside the core start to move faster, creating thermal pressure that resists further collapse. This tug of war continues until the core reaches a critical point around 10 million degrees Celsius. At this temperature, nuclear fusion ignites and the protostar officially becomes a star. But the pressure doesn't stop there. Even after fusion begins, the star continues to grow, pulling in more material from its surrounding disk. This process, known as accretion, adds to the star's mass and increases the pressure at its core. Over time, the star settles into a stable state where the outward pressure from fusion balances the inward pull of gravity. This equilibrium allows the star to shine steadily for millions or even billions of years. What's truly remarkable is how this process repeats itself across the universe, giving rise to countless stars. Each protostar is a testament to the power of pressure, both as a force of destruction and creation. Without the extreme pressures at play, stars, and by extension the planets, life, and galaxies they support, would never come into existence. As we marvel at the birth of stars, we're reminded of the intricate dance between pressure and gravity that shapes the cosmos. Next, we'll explore the pressures found deep within the cores of rocky planets, where similar forces drive geological activity and create the conditions for life. Now, let's turn our attention from the fiery birth of stars to the hidden depths of rocky planets, where pressures of a different kind shape the very ground beneath our feet. Deep within the core of planets like Earth, unimaginable forces are at work, creating conditions that are both destructive and life-sustaining. At the heart of a rocky planet, the pressure is staggering. Imagine the weight of an entire planet pressing down on its center. This is the reality of planetary cores. For Earth, this pressure reaches around 3.5 million times the pressure we experience at sea level. This immense force is generated by the sheer mass of the planet's layers, from the crust to the mantle, all bearing down on the core. But pressure isn't just a destructive force here, it's also a creator. The extreme conditions in Earth's core are responsible for generating our planet's magnetic field. As the core heats up, the molten iron and nickel within it begin to churn and flow, creating electric currents. These currents, in turn, produce a magnetic field that extends far into space, shielding Earth from harmful solar radiation. Without this magnetic shield, life as we know it might not exist. The pressure in planetary cores also drives geological activity. In Earth's mantle, the intense heat and pressure cause solid rock to behave like a slow-moving fluid, creating convection currents. These currents push against the planet's crust, leading to the movement of tectonic plates. This movement is responsible for earthquakes, volcanic eruptions, and the formation of mountains, processes that continuously reshape the surface of our planet. What's fascinating is how these pressures, though hidden from view, have a direct impact on our daily lives. From the magnetic field that protects us to the geological forces that shape our landscapes, the extreme pressures in planetary cores are a testament to the dynamic nature of our universe. As we reflect on the power of pressure within our own planet, we're reminded of its role in shaping not just Earth, but countless other rocky worlds across the cosmos. Next, we'll venture into the vast emptiness of cosmic voids, where the absence of pressure tells a story all its own. Now, let's shift our gaze from the crushing pressures deep within planetary cores to the vast, almost empty expanses of cosmic voids. These regions, often referred to as the emptiest places in the universe, are a stark contrast to the extreme pressures we've explored so far. Here, the absence of matter creates conditions so sparse that they challenge our understanding of space itself. Cosmic voids are enormous regions where the density of matter is incredibly low, so low, in fact, that they are often described as near vacuums. Imagine a space so empty that it contains only a handful of atoms per cubic meter, compared to the trillions of atoms found in the same volume on Earth. This near absence of matter results in pressures that are almost unimaginably low, creating an environment that feels almost alien compared to the high-pressure extremes we've discussed. But why do these voids exist? They are the result of the large-scale structure of the universe, which resembles a cosmic web. Galaxies and galaxy clusters form the dense threads of this web, while the voids are the vast, empty spaces in between. These regions were shaped by the early universe's expansion and the gravitational pull of matter, which left behind these enormous, low-pressure pockets. What's fascinating is how these voids, despite their emptiness, play a crucial role in the universe's evolution. They act as a counterbalance to the dense, high-pressure regions like galaxy clusters and superclusters. Without these voids, the universe's structure would look entirely different. They also provide a unique laboratory for studying dark energy, the mysterious force driving the universe's accelerated expansion. As we explore these cosmic voids, we're reminded of the incredible diversity of conditions in the universe, from the crushing pressures of planetary cores to the near vacuum of these vast empty spaces. The cosmos is a place of extremes. Next, we'll dive into the explosive pressures of gamma-ray bursts, where the universe unleashes some of its most energetic phenomena. Now, let's turn our attention to one of the most explosive events in the cosmos, gamma-ray bursts. These are the most energetic explosions in the universe, releasing more energy in a few seconds than our sun will emit in its entire lifetime. But what makes these bursts so powerful? The answer lies in the immense pressures involved, which are tied to the dramatic collapse of massive stars. When a massive star reaches the end of its life, it doesn't go quietly. Instead, its core collapses under its own gravity, creating pressures so extreme that they trigger a supernova explosion. In some cases, this collapse doesn't stop there. If the star is massive enough, its core continues to collapse, forming a black hole. As this happens, jets of energy are launched outward at nearly the speed of light, producing a gamma-ray burst. The pressures within these jets are staggering. Imagine the force required to accelerate particles to such incredible speeds and to release energy on a scale that can outshine entire galaxies. These bursts are so intense that they can be detected billions of light years away, making them some of the most distant and ancient events we can observe. What's truly fascinating is how these bursts are linked to the creation of heavy elements. The extreme pressures and temperatures during a gamma-ray burst forge elements like gold and platinum, scattering them across the universe. In a way, these explosive events are cosmic forges, shaping the very building blocks of planets and life itself. Gamma-ray bursts remind us of the universe's capacity for both destruction and creation. They are a testament to the incredible forces at play in the cosmos, where the collapse of a single star can unleash energies that ripple across the fabric of space and time. Next, we'll explore the pressures inside hypergiant stars, where the universe pushes the limits of size and mass. Now, let's shift our gaze to the colossal giants of the cosmos, hypergiant stars. These are the titans of the stellar world, dwarfing even the largest stars we've previously explored. Hypergiant stars are so massive and luminous that they push the boundaries of what a star can be, and the pressures within them are nothing short of extraordinary. At the heart of a hypergiant star, the pressure is unimaginable. The sheer weight of its outer layers pressing down on the core creates conditions so extreme that nuclear fusion occurs at a furious pace. This rapid burning of fuel generates immense energy, but it also means hypergiant stars live fast and die young. While a star like our Sun can shine steadily for billions of years, hypergiants burn through their fuel in just a few million years, a cosmic blink of an eye. What makes these stars truly fascinating is how their internal pressures shape their fate. The intense fusion reactions in the core produce so much energy that the star's outer layers are pushed outward, creating a delicate balance between gravity pulling inward and radiation pushing outward. This balance is precarious, and even the slightest instability can lead to massive eruptions, ejecting huge amounts of material into space. These eruptions are not just spectacular to observe, they also play a crucial role in the life cycle of galaxies. The material expelled by hypergiant stars enriches the surrounding space with heavy elements, seeding the cosmos with the building blocks for new stars, planets, and even life. But the story of hypergiant stars doesn't end quietly. When they finally exhaust their fuel, their cores collapse under their own weight, often triggering supernova explosions or even gamma-ray bursts. These cataclysmic events are a direct result of the extreme pressures that define their existence, marking the end of their short but dazzling lives. Hypergiant stars remind us that even the mightiest objects in the universe are governed by the delicate interplay of pressure and gravity. Their lives may be brief, but their impact on the cosmos is profound. Next, we'll venture to the outer edges of our solar system, where the pressures in the Oort cloud reveal a quieter, yet equally intriguing side of the universe. Now, let's journey to the farthest reaches of our solar system, where the Oort cloud stretches out like a silent, icy frontier. This vast, mysterious region is home to countless icy bodies, remnants from the early days of our solar system. While the pressures here are far lower than those we've explored in stars or black holes, they play a subtle yet crucial role in shaping the behavior of these distant objects. In the Oort cloud, the pressure is so low that it's almost a perfect vacuum. Yet, even in this near emptiness, the gravitational influence of the sun and the occasional tug from passing stars create just enough pressure to nudge these icy bodies into motion. Over millions of years, these gentle nudges can send comets on long, looping journeys toward the inner solar system. Comets, those dazzling visitors with glowing tails, owe their existence to the delicate pressures of the Oort cloud. When an icy body is dislodged from its orbit, it begins a slow fall toward the sun. As it approaches, the increasing heat and pressure cause the ice to vaporize, releasing gas and dust that form the iconic tails we see from Earth. But the Oort cloud isn't just a source of comets, it's also a cosmic time capsule. The icy bodies here have remained largely unchanged since the formation of the solar system, preserving clues about the conditions that existed over 4.5 billion years ago. By studying these objects, scientists can piece together the story of how our solar system came to be. The pressures in the Oort cloud may be faint, but their influence is profound. They remind us that even in the quietest corners of the universe, the interplay of forces shapes the cosmos in ways we're only beginning to understand. Next, we'll turn our attention to the mysterious pressures exerted by dark matter halos, invisible structures that hold galaxies together and challenge our understanding of the universe. Now, let's shift our focus to one of the most enigmatic forces in the universe, dark matter. While we can't see it directly, dark matter makes up a staggering 85% of all matter in the cosmos. It forms vast, invisible halos that envelop galaxies, shaping their structure and influencing their motion. But what about the pressures within these dark matter halos? Dark matter doesn't interact with light or ordinary matter in the way we're familiar with, but it exerts a gravitational pull that holds galaxies together. This gravitational influence creates a kind of pressure, though it's not the same as the crushing forces we've seen in neutron stars or black holes. Instead, it's a subtle, pervasive force that keeps stars, gas, and dust from flying apart. Scientists believe that dark matter halos act like cosmic scaffolding, providing the framework for galaxies to form and evolve. Without these halos, galaxies as we know them wouldn't exist. Yet, despite their importance, the exact nature of the pressures within dark matter halos remains a mystery. We don't fully understand how dark matter particles behave or how they interact with each other, making it one of the biggest puzzles in modern astrophysics. What we do know is that dark matter halos are dynamic. They grow and change over time, influenced by the gravitational pull of nearby galaxies and the expansion of the universe itself. These interactions create complex pressure patterns that ripple through the halos, subtly altering the paths of stars and gas within galaxies. Studying these pressures is no easy task. Since dark matter doesn't emit light, scientists rely on indirect methods, such as observing how galaxies move or how light bends around massive objects. These observations provide clues, but they also raise more questions. For instance, why do some galaxies seem to have more dark matter than others? And how do these invisible halos influence the formation of supermassive black holes at the centers of galaxies? The pressures within dark matter halos may be invisible, but their impact is undeniable. They remind us that much of the universe operates in ways we're still striving to comprehend. As we continue to explore these mysteries, each discovery brings us closer to understanding the hidden forces that shape our cosmos. Next, we'll venture into the largest structures in the universe, cosmic filaments, where pressures on an unimaginable scale guide the flow of galaxies and gas across the cosmos. Now let's journey into the vast, interconnected web of the universe, cosmic filaments. These colossal structures, stretching across billions of light years, form the backbone of the cosmic web, connecting galaxies and clusters in a sprawling network. But what's truly fascinating is the role pressure plays within these filaments, shaping the flow of galaxies and gas on an unimaginable scale. Cosmic filaments are made up of dark matter and ordinary matter, threaded together by gravity. Within these filaments, gas is pulled into long, thin streams, creating regions of varying pressure. In some areas, the pressure is high enough to compress gas and trigger the birth of new stars and galaxies. In others, the pressure is lower, allowing gas to flow freely, feeding galaxies and clusters along the filament. These filaments act like cosmic highways, guiding the movement of galaxies and gas across the universe. As galaxies travel along these paths, they're influenced by the gravitational pull of the filament itself, as well as the pressure gradients within it. This interplay between gravity and pressure shapes the distribution of matter, determining where galaxies form and how they evolve. One of the most striking features of cosmic filaments is their ability to channel gas into galaxy clusters, the densest regions of the universe. As gas flows along the filaments, it's funneled into these clusters where it can cool and collapse, fueling the growth of supermassive black holes and the formation of new stars. This process is driven by the delicate balance of pressure within the filaments, which regulates the flow of matter across the cosmos. But cosmic filaments aren't just passive conduits, they're dynamic and ever-changing. Over billions of years, filaments grow, merge, and collapse under their own gravity, creating intricate patterns of pressure that ripple through the universe. These changes influence the evolution of galaxies, shaping their structure and determining their fate. Studying the pressures within cosmic filaments is a monumental challenge. Scientists use advanced simulations and observations of galaxy distributions to map these structures and understand their properties. What they've discovered is that cosmic filaments are not only the largest structures in the universe, but also some of the most influential, guiding the flow of matter and energy on a cosmic scale. As we unravel the mysteries of cosmic filaments, we gain a deeper understanding of how the universe is structured and how it evolves. These immense threads of matter remind us that even in the vastness of space, everything is connected, from the smallest galaxies to the largest clusters. Next, we'll explore the extreme pressures at the event horizon of black holes, where gravity becomes infinite and the laws of physics are pushed to their limits. Now, let's venture into one of the most mysterious and extreme environments in the universe, the event horizon of a black hole. This invisible boundary marks the point of no return, where the gravitational pull becomes so intense that not even light can escape. But what's truly mind-bending is the unimaginable pressure that exists here, where the laws of physics as we know them begin to break down. At the event horizon, gravity doesn't just pull, it becomes infinite. This creates a region of extreme pressure where space and time are warped beyond recognition. Imagine standing on the edge of this boundary, where the force of gravity is so overwhelming that it stretches and compresses everything in its path. This intense pressure distorts reality itself, creating conditions that challenge our understanding of the universe. One of the most fascinating aspects of the event horizon is how it defies our current knowledge of physics. According to Einstein's theory of general relativity, the gravitational pressure here is so extreme that it creates a singularity, a point where density becomes infinite and the laws of physics cease to apply. But this raises a big question. What happens to matter and energy that cross the event horizon? Do they simply vanish, or is there something more at play? Scientists are still grappling with these questions as the event horizon presents a paradox. On one hand, it's a region of infinite pressure and gravity, where time appears to stop for an outside observer. On the other hand, quantum mechanics suggests that information about what falls into a black hole can't be lost. This contradiction has led to intense debates and groundbreaking theories, such as the idea of Hawking radiation, which proposes that black holes can slowly evaporate over time. The extreme pressures at the event horizon also have profound implications for the structure of space-time. They create what's known as a gravitational well, where space is stretched and time is slowed to a crawl. This phenomenon, called time dilation, means that someone falling into a black hole would experience time very differently compared to an observer watching from afar. For the person falling, time would seem to pass normally, but for the outside observer, it would appear to slow down and eventually freeze at the event horizon. Studying the event horizon is no easy task, as black holes are invisible by nature. However, advancements in technology, like the Event Horizon Telescope, have allowed scientists to capture images of the region surrounding black holes, giving us a glimpse into these extreme environments. These observations are helping us piece together the puzzle of what happens at the edge of a black hole and how the pressures there shape the fabric of the universe. As we continue to explore the mysteries of the event horizon, we're reminded of how much we still have to learn about the cosmos. These extreme pressures not only challenge our understanding of physics, but also inspire us to push the boundaries of science and imagination. Next, we'll turn our attention to the subtle but pervasive pressure of the cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe. Now, let's shift our focus to something far more subtle yet equally fascinating: the cosmic microwave background radiation. This faint glow, often referred to as the afterglow of the Big Bang, permeates every corner of the universe. While it may not seem as dramatic as the crushing pressures of black holes or neutron stars, the cosmic microwave background holds a unique kind of pressure that tells the story of the universe's earliest moments. The cosmic microwave background is essentially the oldest light in the universe, dating back to just 380,000 years after the Big Bang. At that time, the universe was a hot, dense soup of particles and energy. As it expanded and cooled, light was finally able to travel freely, creating the first glow of the cosmos. Today, this radiation fills the universe, carrying with it a subtle but pervasive pressure that acts as a constant reminder of our cosmic origins. What makes this pressure so intriguing is its uniformity. The cosmic microwave background is incredibly smooth, with only tiny fluctuations in temperature and density. These fluctuations, though small, are crucial. They represent the seeds of all the structures we see in the universe today: galaxies, stars, and even planets. Without these subtle variations in pressure, the universe as we know it might not exist. The pressure of the cosmic microwave background also plays a key role in shaping the large-scale structure of the universe. As the universe expanded, these pressure differences caused matter to clump together, forming the first galaxies and clusters. Over billions of years, gravity amplified these initial fluctuations, leading to the intricate web of cosmic structures we observe today. But the cosmic microwave background isn't just a relic of the past, it's also a powerful tool for scientists. By studying its properties, researchers can learn about the conditions of the early universe, such as its temperature, density, and composition. This radiation acts like a cosmic time capsule, preserving a snapshot of the universe when it was just a fraction of its current age. One of the most remarkable discoveries from studying the cosmic microwave background is the evidence it provides for the Big Bang theory. The uniformity and temperature of this radiation align perfectly with predictions made by the theory, offering some of the strongest evidence we have for how the universe began. It's a testament to the power of subtle pressures, showing that even the faintest forces can have a profound impact on the cosmos. As we continue to explore the cosmic microwave background, we're reminded of how interconnected the universe truly is. This ancient light not only reveals the origins of everything around us, but also highlights the delicate balance of forces that have shaped the cosmos over billions of years. Next, we'll journey into the atmospheres of distant worlds, where pressures range from crushing to barely there, and uncover how these extremes influence the nature of exoplanets. Now, let's venture beyond our solar system and into the atmospheres of distant worlds. Exoplanets, planets that orbit stars other than our Sun, come in a staggering variety of sizes, compositions, and environments. One of the most fascinating aspects of these alien worlds is the incredible range of atmospheric pressures they exhibit. From the crushing pressures of super-Earths to the wispy, barely their atmospheres of rocky worlds, exoplanets offer a glimpse into the extremes of planetary science. Take super-Earths, for example. These planets, which are larger than Earth but smaller than gas giants, often have atmospheres so dense that the pressure at their surfaces can be hundreds or even thousands of times greater than what we experience here on Earth. Imagine standing on a world where the air feels like an ocean pressing down on you, where the sheer weight of the atmosphere could crush most spacecraft before they even reach the surface. These extreme pressures create environments unlike anything in our solar system, with exotic materials and chemical reactions that challenge our understanding of planetary physics. On the other end of the spectrum, we have rocky exoplanets with thin, tenuous atmospheres. Some of these worlds, especially those orbiting close to their stars, have had their atmospheres stripped away by intense stellar radiation, leaving behind only a faint trace of gas. The pressure on these planets can be so low that it's almost indistinguishable from the vacuum of space. Yet, even in these seemingly barren environments, scientists have found evidence of potential habitability, with some rocky worlds retaining just enough atmosphere to support liquid water, a key ingredient for life as we know it. The diversity of atmospheric pressures on exoplanets also plays a crucial role in shaping their climates and potential for life. On worlds with thick atmospheres, the high pressure can trap heat, creating scorching surface temperatures even on planets far from their stars. Conversely, thin atmospheres struggle to retain heat, leading to frigid conditions that make survival nearly impossible. These variations highlight the delicate balance between pressure, temperature, and habitability, offering clues about where life might exist beyond Earth. Studying the pressures in exoplanet atmospheres isn't just about understanding distant worlds. It's also about learning more about our own planet. By comparing Earth's atmosphere to those of exoplanets, scientists can better understand the unique conditions that make our world habitable. This knowledge could one day help us identify planets capable of supporting life, bringing us closer to answering one of humanity's most profound questions: are we alone in the universe? As we continue to explore the atmospheres of exoplanets, we're reminded of the incredible diversity of worlds that exist beyond our solar system. From crushing pressures to barely their atmospheres, these alien environments challenge our imagination and expand our understanding of what's possible in the cosmos. Next, we'll turn our attention to the heliosphere, the protective bubble of charged particles that surrounds our solar system, and discover how it shields us from the harsh pressures of interstellar space. Now, let's shift our focus closer to home, to the invisible shield that envelops our solar system. The heliosphere, this vast bubble of charged particles generated by the Sun's solar wind, extends far beyond the orbits of the planets, creating a protective barrier against the harsh pressures of interstellar space. The heliosphere is like a cosmic force field, shielding us from the relentless bombardment of high-energy cosmic rays that stream through the galaxy. At the boundary of the heliosphere, known as the heliopause, the pressure from the solar wind collides with the pressure of interstellar gas and dust. This collision creates a dynamic region where the forces of our Sun and the wider galaxy meet, shaping the heliosphere into a teardrop-like structure as it moves through space. The pressure balance here is delicate, with the solar wind pushing outward and the interstellar medium pressing inward, creating a frontier that marks the edge of the Sun's influence. Inside the heliosphere, the pressure of the solar wind dominates, creating a relatively calm environment for our solar system. This pressure not only shapes the heliosphere but also plays a crucial role in protecting Earth and the other planets. Cosmic rays, which are high-energy particles traveling at nearly the speed of light, are deflected or slowed by the heliosphere's magnetic fields and charged particles. Without this protective bubble, these cosmic rays would bombard our planet, potentially disrupting our atmosphere, harming living organisms, and even interfering with technology like satellites and communication systems. The heliosphere's pressure also influences the behavior of comets and other small bodies that venture into our solar system. As these objects pass through the heliosphere, they interact with the solar wind, which can alter their trajectories and even cause their surfaces to erode. This interaction provides scientists with valuable insights into the composition and history of these ancient travelers, helping us piece together the story of our solar system's formation. Understanding the pressures within the heliosphere isn't just about protecting Earth. It's also about exploring the broader universe. By studying how the heliosphere interacts with interstellar space, scientists can learn more about the conditions in our galactic neighborhood and how other star systems might protect their own planets. This knowledge could one day help us identify habitable worlds beyond our solar system, bringing us closer to understanding our place in the cosmos. As we continue to explore the heliosphere, we're reminded of the intricate balance of forces that shape our solar system. From the protective bubble of charged particles to the dynamic pressures at its edge, the heliosphere is a testament to the Sun's influence and the delicate interplay between our star and the wider galaxy. Next, we'll journey to the Kuiper Belt, a distant region of icy bodies that holds clues to the early history of our solar system and the pressures that shaped its formation. Now, let's venture beyond the familiar boundaries of the heliosphere and into the distant reaches of our solar system where the Kuiper Belt awaits. This vast region, stretching far beyond the orbit of Neptune, is home to countless icy bodies, remnants of the early solar system that have been preserved in the cold depths of space. Here, the pressures are vastly different from those we've explored so far, but they play a crucial role in shaping the objects that call this region home. The Kuiper Belt is a treasure trove of frozen worlds, including dwarf planets like Pluto, Eris, and Haumea. These icy bodies are shaped by the unique pressures of their environment, where temperatures plummet to hundreds of degrees below zero. In this frigid expanse, the pressure is incredibly low, but it's not entirely absent. The gravitational interactions between these objects, combined with the occasional collisions, create subtle but significant forces that influence their formation and evolution. One of the most fascinating aspects of the Kuiper Belt is how these pressures contribute to the creation of dwarf planets. Take Pluto, for example. This distant world, once considered the ninth planet, is now classified as a dwarf planet, but its story is no less remarkable. The low-pressure environment of the Kuiper Belt allowed Pluto to retain its icy composition, with a surface covered in frozen nitrogen, methane, and carbon monoxide. The gentle gravitational tugs from nearby objects, along with the occasional impact, have shaped Pluto's surface, creating features like its heart-shaped glacier and towering ice mountains. The pressures in the Kuiper Belt also play a role in the formation of binary systems, where two objects orbit each other. Pluto and its largest moon, Charon, are a prime example. The gravitational forces between these two bodies, combined with the low-pressure environment, have locked them into a unique dance, with Charon always showing the same face to Pluto. This delicate balance of forces is a testament to the subtle yet powerful pressures at work in this distant region. But the Kuiper Belt isn't just a collection of icy worlds, it's also a window into the early solar system. The pressures here have preserved these objects in a near-pristine state, offering scientists a glimpse into the conditions that existed billions of years ago. By studying the Kuiper belt, we can learn more about how planets and other celestial bodies formed and how the pressures of space shaped their development over time. As we explore the Kuiper belt, we're reminded of the incredible diversity of pressures in our solar system. From the crushing forces at the core of stars to the delicate balance in this icy frontier, each environment tells a unique story about the universe's most extreme pressures. Next, we'll take a bold step into the realm of speculation as we explore the pressures that might exist in the multiverse, a concept that challenges our understanding of reality itself. Now, let's take a bold leap into the realm of the unknown, where the boundaries of our universe blur and the concept of reality itself is stretched to its limits. The multiverse hypothesis is one of the most intriguing and speculative ideas in modern science, suggesting that our universe might be just one of countless others, each with its own unique set of physical laws. Within this framework, the pressures that govern these alternate universes could be vastly different from anything we've ever encountered, challenging our understanding of the cosmos and the forces that shape it. Imagine a universe where gravity is 10 times stronger, or one where the speed of light is half of what it is here. In such realities, the pressures within stars, planets, and even the fabric of space-time would operate under entirely different rules. For instance, a universe with stronger gravity might have stars that burn brighter and die faster, creating pressures so extreme that matter collapses into black holes almost instantly. On the other hand, a universe with weaker gravity might lack the pressure needed to ignite nuclear fusion, leaving its stars cold and dark. The multiverse hypothesis also raises questions about the nature of pressure itself. In our universe, pressure is a result of particles interacting within the constraints of physical laws. But in a multiverse, those laws could be so different that pressure might not even exist in the way we understand it. Some universes might have entirely new states of matter, governed by forces we can't even imagine, creating pressures that defy our current scientific frameworks. This idea doesn't just challenge our understanding of pressure, it forces us to rethink the very foundations of reality. If alternate universes exist, each with its own unique pressures, what does that mean for the constants we take for granted, like the strength of gravity or the behavior of light? Could there be universes where pressure is so low that matter never coalesces into stars and planets, or so high that entire galaxies are compressed into singularities? While the multiverse remains a speculative concept, it's a powerful tool for exploring the limits of our knowledge. By imagining these alternate realities, scientists can test the boundaries of our theories and uncover new insights about the universe we call home. The pressures of the multiverse, whether real or hypothetical, remind us that the cosmos is far stranger and more complex than we can currently comprehend. As we wrap up our journey through the universe's most extreme pressures, we're left with a profound sense of wonder. From the crushing cores of neutron stars to the delicate balance of the Kuiper belt, and now to the speculative realms of the multiverse, each extreme pressure tells a story about the forces that shape existence. These pressures not only define the universe we know, but also hint at the infinite possibilities that lie beyond. What other mysteries might the cosmos hold? The answer, perhaps, is waiting in the pressures of a universe we have yet to discover. Now, let's turn our attention to one of the most fundamental processes in the cosmos, the birth of stars. Star formation is a delicate dance between two opposing forces, gravity and pressure. It all begins in vast clouds of gas and dust scattered throughout galaxies, known as molecular clouds. These clouds are the cosmic cradles where stars are born, and the pressures within them play a crucial role in shaping their destiny. Gravity is the force that pulls matter together, causing these clouds to collapse inward. But as the gas and dust compress, the pressure inside the cloud begins to rise. This pressure pushes back against gravity, creating a tug of war that determines whether a star will form. If the pressure is too weak, the cloud will collapse too quickly, leading to the formation of massive stars or even black holes. If the pressure is too strong, the cloud might resist collapse altogether, preventing star formation entirely. The key to star formation lies in the balance between these two forces. As gravity pulls the cloud inward, pockets of higher density begin to form. These dense regions, called protostars, are the seeds of future stars. Inside these pockets, the pressure continues to build as more material is drawn in, heating up the gas until it reaches temperatures high enough to ignite nuclear fusion. This is the moment a star is born, and the pressure within its core becomes the engine that powers it for millions or even billions of years. Stellar nurseries, the regions where stars are born, are some of the most dynamic and chaotic places in the universe. Here, the interplay of gravity and pressure creates a rich tapestry of activity, from the birth of small, dim stars to the explosive formation of massive ones. The pressure within these nurseries not only drives star formation but also shapes the surrounding environment, carving out cavities in the molecular clouds and triggering the birth of new stars in a chain reaction. Understanding the role of pressure in star formation gives us a deeper appreciation for the forces that shape the cosmos. It's a reminder that even the most massive and luminous objects in the universe begin as tiny, fragile seeds, nurtured by the delicate balance of gravity and pressure. As we continue to explore the mysteries of star formation, we uncover not just the secrets of how stars are born, but also the intricate connections that bind the universe together. Next, we'll explore how these extreme pressures impact space exploration and the challenges they pose for humanity as we reach for the stars. Now, let's shift our focus to the challenges that extreme pressures in space pose for humanity's quest to explore the cosmos. As we venture beyond Earth, we encounter environments where pressures reach levels that defy imagination, pushing the limits of our technology and ingenuity. These extreme conditions not only shape the design of spacecraft, but also test our ability to protect human life in the harshest corners of the universe. One of the most daunting challenges lies in exploring gas giants like Jupiter and Saturn. These massive planets are shrouded in thick atmospheres where pressures increase dramatically as you descend. Near the surface, the pressure can reach millions of times greater than what we experience on Earth. Designing spacecraft to withstand these conditions is no small feat. Probes like NASA Galileo and Juno missions have been engineered to endure the crushing pressures and intense radiation of Jupiter's atmosphere, but even these robust machines have their limits. The materials used in spacecraft must be incredibly strong yet lightweight, capable of resisting deformation or collapse under immense pressure. Engineers also have to account for the extreme temperatures and corrosive gases found in these environments, which can degrade even the most advanced materials over time. Every component, from the outer hull to the internal electronics, must be meticulously tested to ensure it can survive the journey and deliver valuable data back to Earth. But the challenges don't end with robotic explorers. Human missions to high-pressure environments present even greater hurdles. The human body is not built to withstand such extremes, and even the most advanced spacesuits and habitats would struggle to protect astronauts from the crushing forces found on gas giants or their moons. For example, Europa, one of Jupiter's moons, is believed to have a subsurface ocean beneath its icy crust. Exploring this ocean would require technology capable of withstanding not only the pressure of the ice above, but also the potential pressures within the ocean itself. Beyond gas giants, the pressures of space exploration also extend to the vacuum of space itself. While space is often thought of as empty, the transition between high-pressure atmospheres and the vacuum of space creates unique challenges. Spacecraft must be designed to handle rapid changes in pressure, ensuring they don't rupture or fail during launch or re-entry. This delicate balance is crucial for the safety of both equipment and crew. As we push the boundaries of exploration, understanding and overcoming these pressure-related challenges will be key to unlocking the secrets of our solar system and beyond. From the crushing depths of gas giants to the icy oceans of distant moons, the extreme pressures of space remind us of the incredible resilience and creativity required to explore the universe. Next, we'll look at how advancements in technology are helping scientists study these extreme cosmic pressures, paving the way for future discoveries. Now, let's turn our attention to the future and explore how cutting-edge technology is revolutionizing our ability to study the universe's most extreme pressures. As our understanding of these cosmic forces deepens, so too does the sophistication of the tools we use to investigate them. From space telescopes to particle colliders, the next generation of scientific instruments is opening doors to discoveries that were once thought impossible. One of the most exciting advancements comes in the form of space telescopes, like the James Webb Space Telescope. This marvel of engineering allows us to peer into the hearts of distant galaxies, neutron stars, and black holes, revealing the extreme pressures at work in these environments. By capturing light from the early universe, Webb is helping scientists piece together how cosmic pressures shaped the formation of galaxies and stars billions of years ago. On the ground, particle colliders like the Large Hadron Collider are recreating conditions similar to those just moments after the Big Bang. By smashing particles together at nearly the speed of light, these machines generate pressures and temperatures so extreme that they produce quark-gluon plasma, a state of matter that hasn't existed naturally since the universe's infancy. These experiments are giving us unprecedented insights into how matter behaves under the most intense pressures imaginable. Looking ahead, several upcoming missions promise to push the boundaries even further. NASA Europa Clipper mission, set to launch in the coming years, aims to study Jupiter's moon Europa in unprecedented detail. By analyzing its icy surface and subsurface ocean, scientists hope to understand the pressures at play beneath the ice and whether this distant moon could harbor conditions suitable for life. Similarly, the European Space Agency's JUICE mission will explore Jupiter and its icy moons, providing new data on the extreme pressures within these enigmatic worlds. Meanwhile, advancements in materials science are enabling the creation of probes and instruments capable of withstanding the harshest environments. For example, researchers are developing diamond-based sensors that can endure the crushing pressures found deep within gas giants. These innovations are not only expanding our ability to explore, but also paving the way for future missions to even more extreme destinations. As we continue to push the limits of technology, the future of studying cosmic pressures looks brighter than ever. With each new discovery, we gain a deeper understanding of the forces that shape our universe, bringing us closer to answering some of the most profound questions about the cosmos. Next, we'll wrap up our journey through the universe's most extreme pressures, reflecting on what these incredible phenomena teach us about the nature of reality itself. As we bring our exploration of the universe's most extreme pressures to a close, let's take a moment to reflect on the incredible phenomena we've uncovered. From the crushing cores of neutron stars to the explosive power of supernova, these extreme pressures are not just fascinating, they are fundamental to the very fabric of the cosmos. They shape galaxies, forge elements, and even influence the possibility of life itself. Each of these 25 facts reveals a piece of the puzzle, showing us how pressure acts as a cosmic sculptor, molding the universe into the awe-inspiring place we know today. Think about it, without the immense pressures at the sun's core, nuclear fusion wouldn't occur and life on Earth wouldn't exist. Without the crushing gravity of black holes, we wouldn't have the mysterious phenomena that challenge our understanding of physics. And without the pressures in the early universe, galaxies and stars might never have formed. These forces are not just extreme, they are essential, but the story doesn't end here. Every discovery raises new questions, and every answer leads us deeper into the mysteries of the cosmos. What other secrets do these extreme pressures hold? Could they reveal clues about the origins of the universe or the nature of dark matter? The more we learn, the more we realize how much there is still to explore. So, as we wrap up this journey, I leave you with this thought. The universe is vast, complex, and full of wonders waiting to be discovered. What fascinates you most about these extreme cosmic forces? Let me know in the comments below. I'd love to hear your thoughts. And if you enjoyed this deep dive into the universe's most extreme pressures, don't forget to hit the like button, subscribe, and ring the notification bell so you never miss out on our next cosmic adventure. Together, let's keep exploring the mysteries of the universe, one fact at a time.